Hello everybody, welcome to our talk, Capturing the Reality of Space with RTX in Deliver Us the Moon. My name is Daniel Torkar, I'm the technical artist at KOKAN Interactive.
Hi, I'm Vladimir Bondarev. I'm a dev tech at NVIDIA, and I helped these guys.
And my name is Cohen Dietman. I'm the CEO of KOKAN Interactive, and it was a blast working with NVIDIA on this.
So we're going to be talking about how we implemented ray tracing in Deliver Us the Moon, what optimizations we did, and that's what I'm going to be talking about a little later in the talk. Koen is going to talk more about why it's a smart idea to do that, regarding marketing and all those such things. And then Vladimir is going to talk about more in depth of how does ray tracing work in Unreal.
Yeah, I'm going to talk a little bit more in depth about opaque reflections and hopefully help you guys to understand how it works and improve your game performance.
Perfect. So let's get going. So we're going to start talking about content optimization for ray tracing in UE4. The original content in our game is designed for conventional rasterization and delivers suboptimal ray tracing experience. Most problems are jittering in reflections, so small sparks that should not be there, low frame rates, which obviously is a problem in games, and high RAM usage. For example, where our landscape was completely loaded in, but it didn't have to be. It could just be loaded out and nobody would notice. We're going to be optimizing our game to figure out where most of the performance has gone and how we can optimize our content to work better with ray tracing and make it compatible with that. So, from start to finish, here you can see on the left side that our game is running at around 40 to 50 FPS and has some stutters which are really jarring. And on the right side, we optimized our content. And you can see that we have an average about 93 FPS. This is without DLSS, and the difference is about 40 FPS. We went from 51 FPS to 93 FPS on a 2080 Ti on 1080p. And that is why it's so important to optimize your content, so you can get these huge performance gains and still keep the visual fidelity of ray tracing. Okay, starting off, you need to figure out where to optimize. Obviously, that's what this whole presentation is about. So, where we started, we went through the project per level to figure out what materials we used mostly and to see where we could gain most. And we found out that we didn't have a lot of materials, a lot of material instances, but very few master materials, which saved us a lot of time in optimization because we mainly had to focus on one material. In that optimization of materials, the ray tracing quality switch now is crucial. That is your one and only thing in which you can define how a material can look different in ray tracing. The next step is to just disable all ray traced shadows and lights to start off, because that gives you a base idea of what the performance can be and in which scenes you have the budget to actually enable ray trace shadows for possibly area lights, because you need to find out what brings most visual improvement. Some scenes might not need certain aspects. For example, ambient occlusion and global illumination are baked in our game, so we had very little to gain to use ray traced global illumination and ray traced ambient occlusion. So we chose to not use those. So the most important thing to optimize is reflections and materials, and the reflections of those materials, really. We're going to start off with some opaque materials, see what we can do to optimize those, then move on to translucent materials, which have a lot of similarities, but a few key differences. We're also going to talk about the MIP bias, which we use to reduce the used memory bandwidth and improve texture caching. Also going to talk about normals and how we can reduce the noise in those, the high frequency noise in particular, to make sure that the reflected images look crisp and clear. In your materials, you will want to have less complexity, so simplify where you can using the ray tracing quality switch node. And in the end, we're going to talk about hybrid translucency shortly to figure out how we can enable more particles, or just any particles at all, really, to be visible in your game without having a very heavy cost on performance. Okay, so what you can see here is what we are aiming for. Minimum visual difference with better performance. On the top half, we have a huge reflective mirror that shows these two planes on this side. These two look exactly the same, but mirrored. And at the top, you might see some differences. But the idea is that it's so minimal that it's barely noticeable. For example, you can look yourself now and see what differences you can notice. I'm going to tell you. In this one, we have optimized a lot of stuff. There are no normals, no baked ambient occlusion, and we added a MIP bias to a lot of the textures used. And on the top left, everything is left unoptimized. Opaque materials. That is where we started. We looked at our scenes and found that this one material you see on the side is the one that we use the most. So it's a great example. And mostly based on this one, we decided on what our maximum roughness would be for the cutoff to get ray trace reflections in opaque materials. In Deliver Us the Moon, we set the roughness cutoff value to 0.36, which is specific to our game and will vary depending on your game. It's a value that decides whether reflections get ray traced or fall back to conventional non-ray traced methods. The main problem we had with some of our high frequency normals was that reflections gave very grainy and jittery reflections of emissives in the environment, and that looked very bad. So reducing that high frequency noise helps you mitigate that. Important to note is that our game sets roughness in the shader to 0 if the regular roughness is anywhere below the cutoff. What this does is our roughness for everything that is ray traced is actually at 0. That gives us cleaner reflections and better ray coherency. Another thing to consider is that if texture has a very low value in your visual representation of your material, then you should consider removing it entirely. So, for example, in here, we removed the normals and the baked ambient occlusion to reduce the memory bandwidth. Another thing that helps is just simplifying all the logic in your materials and reduce all the complexity as far as you can. Yes. So, in here, you can see me in the engine, and I'm going to show you what happens if you change the roughness cutoff. And keep in mind that in our engine version, we changed that everything below the cutoff will get a roughness of 0. So here, changing the cutoff to 1 will make everything have a roughness of 0 in the rendering and reflect. And now I will zoom in on this thing here. And that's where you see most of the difference. You see that it reflects everything. And this, albeit it might look good, it is definitely not optimal because everything reflects, and that is not realistic nor good for performance. So I'll show you how in this material we change most things. It's a relatively complicated material. It's not too much, but it was too much to actually use. Here you can see I completely removed the normal, just put a 001 when it's ray traced. And here also, the ambient occlusion is completely removed when it's ray traced. And this is how you mainly want to use the ray tracing quality switch replace node. This is the normal calculations, the blends, the detail map, and the regular normals. Or we throw that all away when the material is ray traced. And remind you, this is only in reflections. So this is not how the material normally looks. This is how the material looks in reflections. Another thing we used is a MIP bias, because we have several high-resolution textures. We use a whole texture atlas for this material. And here you can see the MIP bias when ray traced is 2, which means that it's 4 times less intensive. You have more cache hits, which improves the performance. And we use that for this texture, for another texture over here, I think, and over there. So we use it extensively, and using it in multiple places just continuously improves your performance. Of course, you need to figure out what actually helps and what doesn't damage your visual integrity of your game. You want it to still look like your game. You don't want to do too many concessions, and luckily you don't have to. Translucent materials. In translucent materials, the primary and the secondary ray are both ray traced, which means the ray tracing quality switch node can be used immediately to optimize the material, not only in reflections. Again, flatten normals and reduce the high frequency noise in those. Noise is bad for ray coherence, which will be talked about later by Vladimir. Reducing your texture usage helps immediately, because every ray that hits a window, for example, immediately uses that texture, and not only in reflections. And thankfully, our glass doesn't need much textures, and it's mostly about the Fresnel and the reflections of other materials. Also, less logic is better. The simpler, the better. So use the ray tracing quality switch node anywhere you can. So, in this window, you can see me in one of our scenes. And we have huge windows here that reflect the scene. Ray tracing is now off. You can see the screen space reflections. Ray tracing is on, and you can see the whole room reflecting. You might also notice that we removed many of the normals. These normals, these lines, for example, are not visible in ray tracing. And we did that to optimize, obviously, not because it looks a lot better, but it does give you a cleaner and visually nicer reflection. And here is the material graph for our glass. You can see here, completely remove normals. Again, just like the opaque materials, only this time they work on the first ray and not only when the material is in a reflection. We also found some spots where we thought it would be useful to have a different value for the glass based on if the game was ray traced or not, since it uses the first ray to ray trace. Well, since the first ray is also ray traced. For example, we could set different colors for the glass, because otherwise the glass might seem too light or too dark because the reflections differ. It's not very productive to continually use the console, so I made a quick hot bar in which you can see what is enabled and also switch the settings. Translucent materials are used a lot in particles, and which makes it a slight issue. Cascade, the older Unreal particle system, doesn't support ray tracing. So we had the choice to just recreate some effects in Niagara, which is a lot of work, but then our particles would be visible in ray tracing. But it also took a lot of performance. Many of our particles are just translucent materials floating through this air. And in the next slide, I will show you what happens without a specific technique called hybrid translucency. We needed something for our particles to be visible in the game without being ray traced, because ray tracing them after converting them from Cascade to Niagara proved to take away a lot of performance. So thanks to NVIDIA's 423 branch, we took hybrid translucency and implement it in our version of the engine, the Unreal Engine. And this made it so that only the front translucency layer would be ray traced, and the remaining layers will be rasterized. And we use this to exclude our particles from ray tracing. So in this scene, you can see our particles hanging in the air, and they look square. And that is because the first ray gets ray traced, but behind that, there is no ray tracing. Everything gets rasterized. And that is why the glass behind the particle technically looks wrong. So here you can see me putting the refraction rays to 2. And what that does, it helps, it fixes the problem, because the ray behind the particle also gets ray traced, as is normal for the rest of the glass. So you don't see that square image anymore. Adding an extra ray increases our frame times by about 0.18 milliseconds. And that is unacceptable for just a few particles floating in the air. So what we did, we implemented hybrid translucency, which allowed us to exclude our Niagara system from ray tracing, but still be visible by being rasterized. And then the particles are rasterized, give good performance, but there are no artifacts whatsoever. Lights and shadows. In the beginning, we disabled ray tracing on all our lights. And now we have arrived at the moment where we pick and choose which lights we want to enable ray tracing for. We chose our sunlights mainly because those affect the whole scene in one go and give you many detailed shadows in places where you really want them. Another thing is area lights. They are very pretty, but they are also very costly because the light comes from a whole area. And instead of being from a point, you need to denoise the shadow that comes from it. And that denoising can be costly. Another thing that ray trace shadows enables is a very fast workflow. You don't need to bake your shadows anymore. You immediately see the feedback from the attributes you change in your lights. Here we can see in this scene our ray trace directional light. There you see it, sun, and it shines through this mesh fence. And this is a mask material, and it shines very detailed shadows on the ground. And now I'll show you if we disable ray tracing. All the detail is gone. It's just only baked shadows that don't look very good. The same goes for this grate. Now it's just the texture, the light map resolution is too low to catch these kinds of details. So that's why we opted for our ray traced sun shadows. Now I'm going to a scene that has an area light, very specifically chosen because it's a small scene, there is no ray traced lights close by, and the detail really adds to the depth of this small diorama kind of thing. Here you can see the lights on the left from the wires, the screwdriver, and the mug, the difference between ray traced and non-ray traced. This is ray traced, very soft shadows ending, and moving it, you can see it move immediately, no time to wait, you don't have to bake anything, no need for crazy high light map resolutions. Right, so why did we take the chance to, right before development ended, to still opt for ray tracing? Well, eventually we found out that it's relatively easy. It took us about two and a half months to get it release ready. Next to that, this new tech experience is extremely valuable. We believe that ray tracing is the future. Many companies believe it, and NVIDIA helped us a great deal with getting into the future, really. And last but not least is the marketing value. Working together with a great, huge partner like NVIDIA really enables us as a smaller studio to lift up anybody's experience and visual fidelity of our game. And about that marketing value, Cohen will tell you all about it.
So where did we benefit? Well, first of all, we were the only indie with ray tracing in 2019, releasing with it, also in Unreal Engine. So that was already value on itself. Second of all, you know, NVIDIA is a large company, so we were included in their large marketing campaigns. So thinking about their social media, speaking about it occasionally, or you know, being shoulder to shoulder to large games such as Control or Wolfenstein Youngblood or Call of Duty Modern Warfare, that is, as a small indie, of course, very interesting and very valuable. So, and I can imagine that if you are an indie at home right now or wherever you are in the world and you looking at this, thinking like, of course, well, how do you make a decision like this? Is this something you just do, you know, it can feel or come over as a little bit intimidating. So what I would say is, of course, this was a serious investment for us as a small company, because of course we could have relocated some of the resources on something else or other projects. But I thought, like, if you would look at the future and see, for example, how consoles are getting ready for ray tracing and stuff, this was a serious conscious choice for us to benefit from being one of the first, working together with such a large giant, benefiting from their marketing power in that sense, and yeah, investing in our future to have actual knowledge about this tech. So in my opinion, I would say, if I take a look and as a retrospective, I would say it was relatively easy, but it's something that sometimes can intimidate you, but I wouldn't be too scared for this.
Hello, my name is Vladimir Bondrev. I'm a DevTech engineer at NVIDIA. I would like to extend Daniel's and Koen's presentation with some extra information. What we're going to talk about is about how to decompose the ray tracing reflections and to understand how they work. And this will allow you to adjust your game performance in such a way that your game will run faster, but also you will be able to maintain your visual quality. The goal of this presentation is to also equip you with the same knowledge which Daniel and Koen have to improve their game performance. This knowledge consists of understanding how the reflections in Unreal Engine work. Then those reflections will be decomposed in small parts, and those parts you will be able to understand how much they cost on the GPU. Once you understand that, you also are able to understand how your scene behaves, and this knowledge will help you to take an appropriate action. After you have the appropriate knowledge, we are going to take a look at this scene to perform a performance decomposition. Okay. So I would like to start with helping you understand how reflections work. It is maybe basic for most of you, but it is crucial to know what it actually does. So Unreal Engine makes a chief distinction between the translucent reflections here and the opaque reflections here. They're relatively dissimilar, with an exception that the translucent reflections have refractions. So it goes from one material, refracts through one material, performs reflection, goes on to the next material, performs reflections, and so on. While the opaque materials have only the reflection. Also in this presentation, I'm only going to cover opaque reflections because they are so similar and much more easier to understand. Once you understand the opaque reflections, you will be also able to understand how translucent reflections work. All right, let's move on and see how the reflections work in Unreal Engine. Here on the left, you are seeing a 2D ray tracing representation. And on the right is the representation of Unreal Engine's shader code and its flow. So we're going to go step by step how reflection is created, and this should help you understand how it all works. So what happens first is that a scene gets rasterized into the G buffer. This acts also as a primary ray, which means in ray tracing you don't have to do that, and we only need to be able to construct a reflection ray. So to construct a reflection ray, what needs to happen is that the RayGen shader needs to be started or executed, and once it's executed, you need to load all the necessary data from the G buffer into the RayGen shader for the corresponding reflection pixel. And with that reflection pixel, you will be able to construct a reflection ray, here, the red. And once the ray is constructed, you then use the ray tracing API inside the shader to perform a ray cast. Once the ray is casted, right, here for the reflection, it will be intersected or missed. But in this case, it's intersected. When the ray is intersected, a closest hit shader is loaded and evaluated. When the closest hit shader is evaluated for your material, then its output data, such as base color, roughness, or for example, world normal, is stored and then packaged into the payload package and then transferred back to the RayGen shader. It's actually, so the RayGen shader creates those rays, it casts them to intersect with some geometry, like here, and after it intersects it, it evaluates your material in the closest hit shader, and the data which is evaluated gets back from the RayGen shader to the, gets back from the closest hit shader to the RayGen shader. And we call this usually, let's see, the payload package. So when the data is back of that material to the RayGen shader, this data is evaluated for each light. So once the payload package is back to the RayGen shader, each data is evaluated for lighting. And this is done for each light. So what actually happens, there's a loop which iterates over this data, and also based on the type of light, and also based on whether this light is able to cast a shadow, right, from here to there, it is also tested for occlusion. So if the light is occluded by some geometry, it's not lit. But it is tested, so it also costs ray tracing rays. Ray casts. It also costs ray casts. Right. And this process is actually repeated over and over until the maximum number of bounces, right, bounces is reached, or the number of samples per pixel is also reached, or the ray actually misses. And when the ray misses, your skybox, for example, is sampled instead. The ray bounce also stops when the evaluated material roughness is also higher than your maximum roughness, because then this will be offloaded to the environmental probe. Finally, the data is then stored into the reflection buffer and evaluated in the end and composed into the final image. All right, now that we know how ray tracing or opaque ray tracing works in Unreal Engine, with that knowledge, we try to understand how each subpart of that algorithm works. So we want to understand how much total cost is, then we want to understand how much performance do we pay for the reflections and how much for the light visibility. And we also are interested in how much of this cost, the total cost, is represented in this whole scene. So how much of those pixels are actually ray traced. You can do that by using Unreal Engine command called stat.gpu. What it will do, it will show you a table. This table contains different GPU time metrics, and one of those is the opaque reflections in Unreal Engine. In this case, it's ray tracing reflections, and it costs 5.31 milliseconds on a frame, the whole algorithm. Now that we know it costs 5.3 milliseconds, we want to know on which surfaces which we're seeing in the scene do we pay the cost of 5.3 milliseconds. You can do that by using this command. What it will do, it will visualize the reflection buffer, this buffer, but it also will multiply it with a very high value, which is stated here. And it will result that you will be able to see all the reflections in the buffer. And this will give you a quite good representation of surfaces which are reflected with ray tracing. So, doing so, for this particular scene, not only this what you see here, but it goes actually beyond here, but it's cut off. It's in total 31% of the screen is covered with ray traced reflections. So this is the cost which you're paying, 5.3 milliseconds for 31% of your screen. So what determines this coverage of your screen? So as Daniel already explained, this is caused by the definition of your max roughness and the output value of your evaluated material. So the base value which is used in Deliver Us the Moon is 0.36, and in this case, only for this particular image, it's approximately 35%. Actually, it's a cutoff of an image. There's a bigger image. When you would lower that value, right, then you will get less ray traced reflections, which result in lower coverage. So lowering the maximum roughness to, for example, 0.32 will result there in 90% screen coverage. This will also result in cheaper reflections because you have less pixels to be evaluated for reflections by ray tracing, but it might also reduce your visual quality. Not sure if it's good or bad. That's up to you to decide. If you would increase the total max roughness, it will also increase the maximum coverage to, in this case, 50%. As Daniel already showed, having everything ray traced is not necessarily a better looking image, but if you know which parts really contribute to the final image and which don't, you can judge based on that to select correct roughness. So, knowing that information, you should ask yourself which surfaces should be ray traced and which not. Does it make sense to have the surface reflected with ray tracing or not? And let's take a look at the following example. So there is this metallic tile and it has some form of raster in it. So does it make sense to have it almost completely ray traced reflections? Does it make sense? If you look at the image, the black surfaces on the raster are nearly not visible when they are reflected. However, the reflection image shows they are definitely reflected. So it might make no sense to reflect that. Instead, what you could do is increase the roughness. You will offload that to the environmental probes, while the detail which really matters for ray tracing, like the outer part of the raster or whatever, this will contribute to the final image, and this makes sense to have. But again, this is up to you to decide. So we know how much percent of your screen is now covered by the ray traced reflections. We know the total cost. However, it is also important to understand and what roughness does. Roughness not only is responsible to cut off the threshold where your reflections are ray traced or not ray traced. It is also important to understand that the value of your roughness also determines the ray coherency. And Daniel already mentioned what ray coherency means, but he didn't go into the depth of it. He left it to me, and let's dive into that because it can be very important and actually a game changer for your performance. And you will see the reason why. So in this image on the left, is a surface which is has a low roughness, and here is a surface with a higher roughness. So a higher roughness results in a larger sampling cone, and a lower roughness results in a lower sampling cone. So each time the ray is reflected, each time it is randomized within that cone where it should reflect. This means that every time the ray is hit, it is somewhere in that cone and it will intersect somewhere in that geometry there. So the smaller the sampling cone, the better ray coherency. The larger sampling cone, the worst ray coherency. Normals are also related to this, but to the neighboring pixels and not the same sample. All right, so let's see actually what this in theoretical example means. As you can see, the lower roughness, 3 of those rays reflect and sample the same data. It hits the same box. However, the rough surface within that bigger sampling cone, it reflects and samples from 3 different data sets. So this means that higher roughness also has better cache utilization. And better cache utilization with lower roughness improves your performance because the data, such as geometry, shader, or texture, is already in the cache and it doesn't need to be fetched from VRAM. So it goes much faster. All right, now that we know how ray coherency works, and with this theoretical example, let's look at a practical example from the game. So in this example, you're seeing a rough glass with normal maps, etc., and roughness maps. And in this example, roughness is removed, and also the normal maps, because you don't need them there. And this also allowed to make the shader simpler. A result for this particular scene, just only for the reflections of these materials, result in up to 20% performance win. And that's a lot. So please consider the ray coherency when you're working with the materials. All right, now that you know how ray coherency works and what it is, please take this into account and let's go back to the opaque reflections. Now that we know how ray coherency works, we know the surface area which is reflected, and we know the total cost of the reflections, we want to be able to understand what's actually going on in each pixel which is reflected. And we have to look at the reflections themselves, right? But also at the light. We're going to start with the lighting, so direct lighting. And in this scene, the lighting is right now on. And if you look at this reflection here, so on the blue floor of reflection of the cabinets, if you would switch off the lighting, there will be less light inside the reflections, and the reflection in the image will be almost gone, but still a little bit visible here. See, it's almost disappeared. When you turn off and turn on direct lighting with this C-bar, you will be able to measure the difference in the performance in the start GPU, and this results in total of 2 milliseconds performance cost. Right, now we know that our lighting costs 2 milliseconds. But we want to also know where do we pay those 2 milliseconds for. Those 2 milliseconds goes actually in total of 64 lights. And this entire scene, like not the complete level, but this specific scene has loaded 196 lights, which is almost 200 lights. And however, the ray trace lights support only 64 lights at this moment in Unreal Engine 4.23. And out of those 64 lights, we have 21 shadowed lights. And those shadowed lights are actually responsible for creating those ray casts, which obviously are not free. So what can you do to improve that? You can decide reducing the number of shadowed lights, or perhaps you can decide to reduce the number of lights in total. So if you would reduce the number of lights, you will start from no lights reduced, 64 lights, 0 reduction, then 32 lights, it's half a millisecond reduction, 16 lights, 3/4, 8, 1.1 millisecond, and then no lights, 0 lights, 2 milliseconds. So what is the most beneficial for your scene? Visual quality wise and performance wise, it's up to you. However, 0 lights is usually not the choice because your scene will not be lit. In case of Keioken, they chose 8 lights. It resulted in good image quality while still having sufficient performance. For some scenes this might work, for others not. You should experiment with that, what's best for your scene. So whether you choose 64 or 16 or 8, that's up to you. However, to be able to do that, Unreal Engine 4 stock version doesn't have that ability yet. Not sure if it will come, but we have our own NVIDIA RTX 4.24 branch, which supports a CVAR and allows you to set the maximum number of lights. So yeah, go check it out. All right, so we know now that the lighting cost is in total 2 milliseconds. Now we're interested in actually when we perform the reflections, how much does the material of those reflections cost? So the question is, what you're seeing here in these reflections, of those cabinets, how much performance does those reflections cost if you disable the material? So disabling the material, what it will do with this CVAR here, it will actually replace all the material instances with only one single, very simple material. And it will look like that. So actually you do have reflections here, but the reflective material is black, which has nearly no contribution to the final image. And this difference in performance is 2.1 milliseconds. Bear in mind that it's when you replace all the material instances with only one material. In practice, this is not realistic because your scene will contain many different materials and you want to actually be able to understand the impact when you adjust your materials instead of removing them completely. As Daniel explained already in his presentation, that they were fortunate enough to think of a good material setup, and they already have like a couple of master materials which can be tweaked, and this will touch many different material instances. So you have to start at adjusting your master material to find out actually what it costs. And you can do that by simply opening that material, and as you can see here, the input nodes, what you have to do is replace all those nodes with ray tracing quality switch replace. And final image, or at least final material, which you will be benchmarking, will look something like that. So everything, all input is replaced. And for example, when we look at here, so this is with original material, no replacement. And this is when everything is replaced. Because the material color is white, it's very well reflected. But it's totally not representative of the final image. But with this, we are totally able to measure the performance cost of that material. So its complexity, its texture loads, its size, it all contributes to performance difference. And we are now able to see, if we strip it to like bare minimum, what it will cost. And this cost is 0.29 milliseconds. So if you would simplify that specific material, that master material, you will not be able to get more than this. This is like the total max. So this will help you to understand whether it's worth it to adjust or is it not worth it to adjust. It's a decision which you are able to make. However, in this scene, it's totally worth it, because there are also translucent reflections, and those materials are also reflected there. So if you adjust this material, you win on opaque reflections, but also on translucent reflections. It's a cumulative effect. So in this case, it's 0.29 milliseconds plus 0.13 milliseconds for translucent reflections. In total, it's 0.24 milliseconds performance win, total performance win, which you can win. Of course, in practice, you will not strip it completely down, but you will simplify it to a certain level where it will still matter. All right, so after having this knowledge, and the same knowledge which guys from Keoken have, they were able to improve the scene coverage, so decide which parts of the scene matter most and cut off those that contribute less. They were able to improve the ray coherency, so that the ray faces more or less the same direction, and also reduce the number of lights, and then also simplify the materials. So the lights are not switched off, they are still there. The materials are all there, but they are somewhat simpler for ray tracing. The rays are better, and the coverage is better. This in total results from this image to that image. So you do see that there is a light gone here, but overall lighting is fine. And the total performance win with this particular changes is 2.24 milliseconds, which is really, really significant. And this is also only for opaque reflections. This also happens for translucent reflections. So there is also a number added to this, which is reduced in performance cost. So this is what you can achieve if you try to optimize your content and carefully evaluate how your materials behave. All right, now that you know how you can create your own performance decomposition of opaque reflections and then take appropriate action to improve your performance and also maintain your visual fidelity, I can give you also an advice to try to take a look at our NVIDIA RTX branch, which has many different optimizations to help your game perform better. And also there are many, many different optimizations coming. So if you're interested, please take a look at this link here. Then also an important part which played quite a big role in shipping Deliver Us the Moon is DLSS 2.0. So here's an example of 3 images, the same images, but with different anti-aliasing techniques. Are you able to guess which of those techniques is actually DLSS? On the left, there's no anti-aliasing at all. Here is high version of tempo anti-aliasing from Unreal Engine itself. And in this case, is DLSS performance mode. On both images here, you are unable to read what's in there, and of the DLSS version, you're almost able to read what's written in there. And in addition to its visual fidelity, you also get a great performance improvement. So for more information, you are welcome to take a look at videos and dev blog posted by NVIDIA later on. If you have any questions, please feel free to contact us, and we will be able to answer anything we are able to. So don't be shy. All right, thank you for watching. I hope that you can use this information to improve the performance of your games and deliver great titles.
Thanks for watching, guys.
Thank you.
See you next time.